Pleasure to be here. It's been a fantastic conference. I think I've commented a couple times that our entire group in Canada should have been here. This has been a fantastic learning. And again, I think one of the things I appreciate the most is I'm used to talking to an audience where I'm the one guy on the soapbox. All of you have the same soapbox. I'm very happy to have us in the same room. What I'm going to talk about today really talks about how we've been applying automation to really democratize organic synthesis. And the goal here is to take expert abilities, such as the ability to make complex small molecules, and really push that out to anybody that needs to build it. So what we're talking about is, if there's a physicist that needs a specific molecule for a conductive polymer, they shouldn't need to have a full PhD in synthetic lab in order to do this. This is really about taking those skill sets, allowing people to dream broadly and use those sorts of areas of technology for their own research. So this is crossing boundaries in interdisciplinary research. The main challenge behind this, though, is that it's taken a while. The general loop that we typically would go through looks like this kind of a general process. Any sort of reaction that we endeavor to do is going to have a process to look at a reagent preparation, execution, and monitoring. And really, it's through these kinds of unit operations, very much like our opening talk today, individual aspects of a synthesis come down to understanding what's necessary for that reaction, embedding that, and making it flexible enough that we can change those different steps. So what's being shown here is basically this was me as a graduate student. It was a kinetics, physical organic sort of setup. So it has to have the ability to do certain things like charge powders, change the actual solvent as necessary, do mobile dosing, so picking up a radio-controlled doser to actually be able to interact with HPLC, but also move samples between different places and actually change initial conditions based on needs. So instead of running a grid of experiments, it's adapting to a specific environment and then changing its reaction trajectory based on individual outcomes. And we've done this. A lot of us in this room have built these kinds of parts where, again, maybe you're thinking about getting to a particular starting material. Now, typically, this is done by going to the literature or going to vendors. Barring that, if that doesn't exist, we go to synthesis planning. So this is where we stretch out to databases where prior knowledge says that this molecule or one similar to it could be taken. And if that fails, then what you do is go to the primary source, maybe an expert synthesis team, and then actually have to physically build in one place and ship somewhere else. There's a geographic translocation that has to happen there too. That's where we start to have physical movement of molecules. And in fact, what I'll wrap up with today is a little bit of a highlight of a project we were in where this is also very, very common, that the physical location of materials between different places, the barrier to our synthesis, the real bottleneck, becomes things like customs, shipment failures, and other things in that point too. So the ability to actually take synthesis and fully digitize it, the dream here is to take something like what we've seen in rapid fabrication, something like a 3D print. It's very easy to build a digital object, share that somewhere else, and because of data standards and standard hardware, you can reliably, or at least reproducibly, take a digital object and fabricate it somewhere else just by this change of data. This is as close as we get to the Star Trek kind of world of the synthesizer, right? Go into your point, Earl Grey, hot, and you have exactly what you've demanded reliably in any space. The problem is we have, especially in organic synthesis, there's a domain level of expertise that we encode our information in something that's not very conducive to synthesis, especially under different environments. So even in this procedure here, you have very abstract kind of soft variables, things like stirred vigorously and filtered until it was concentrated. These don't have quantifiable endpoints. These are domain-specific language to people that are in the know that understand what that might mean, but still leaves open to interpretation. Then you have other hard variables, time and temperature. However, even that, the reason that you have 4 hours at 25 degrees is because there's a specific outcome they were trying to achieve. It's not that there's something magic about that time and that temperature. This happened until a certain reaction endpoint was achieved, which may be different if you have a different batch of starting material, slightly different reactor geometries. So these outcomes being fixed in this way is not even actually the real intention for why it was written down. We actually want to sort of extrapolate this back to more why the reaction was done in the first place. So really to do this, we kind of focused, and what I'm going to talk a little bit about today is kind of what has to be developed in these two areas. And one of them, as we discussed earlier today, is the ability to embed autonomy in what we're doing, so decision making. And the second is standardization between different components, or the ability to use different hardware in different ways. So in this first example, this was a paper done by one of my earlier students, Junlang Liu, who built a system that was based on adaptation. So it had the capabilities of doing many different steps, but more importantly, it could adapt to circumstances. So this is a concept that a collaborator at Amgen, Dan Griffin, came up with, where he tried to liken the idea of synthesis under autonomy in the same way as the problems that you run into a full self-drive kind of a car. If you take the task of driving from a place to a place, and you break it down to the individual autonomous steps, such as the position of the wheel, how much thrust you may have to apply, how much brake, and you sort of break that into a series of rote scripts and asked it to have an outcome, such as driving from downtown Los Angeles to someplace in the north, you could reliably record one result and replay it. So that's the simple automation of that action. However, if you were to take that and put it into a complex environment, and ask it to do the exact same thing, you'd probably run into some major problems. So this is an idea that you can't just simply break down a simple automated action into a simple script. It has to adapt based on circumstances, so you have rules and goals rather than a specific outcome. What you're asking it to do is move from a place to a place, following a set of rules, and make decisions on the fly. So in that same concept, what we had was this challenge where our goal was to measure the rate of coupling after activation of some carboxylic acid with some amine. And we needed to measure each one of these absolute rates. So we're not just looking at the reaction between these two, there's a precursor step that has to be done individually for every one of these molecules. And the problem with this from a physical organic standpoint is you're talking about 340 possible combinations. In triplicate, it's over 1,000 reactions, and every one of them becomes a bespoke optimization that you have to execute. As a graduate student, in your lifetime, you might get through 10 or 15 of these. So from a data science perspective, this is what we needed. We needed this information, but it's unlikely to have a person grinding out, and as, again, great comment from this morning, your job as a PhD is a data point in an AI model, and that's very depressing. What we did is we looked at this from the perspective of, again, adaptation. In this particular case, this is something that happens very common in all synthetic steps. You have a first step, which has a conditional outcome. This reaction has to run with a certain amount of a material, producing products and producing this intermediate. The time and conditions for that have to vary, where the outcome is full consumption of this material. And the second step has to only be initiated once the first conditions are met. The thing is that, again, these are two steps where the outcome from the first one, the conditions, actually impacts the second one. And why this becomes a challenge for autonomy is, again, any small variation or any small failure can lead to disastrous consequences following on. So this is a very infamous hot dog making robot that very early after all its position misses its first step in terms of the bun placement, and then after that it's just moving on, assuming that everything is well and true, where really what you've done is completely missed the point after that. So these small things, watching robots fall over and bang into things, are hilarious. We like to do this in the area, but this is a reality of what happens. It's because how we view the steps is by taking the sort of anthropomorphic what you would do in the lab, and then just simply coupling that together, putting it on replay. Instead, what we focused on in my group is spending a lot of time on the analytical chemistry by giving the robot the ability to see the reaction in its sort of reaction space. So we use things like online HPLC, online React-IR to measure compositional data about the reaction as it's happening, and then to have that as a change. So here what we would have is maybe the change in concentration of material to this intermediate. If we know or set a sort of a loss of this, where the loss of that sort of material informs us that we've made the product of choice, we then know the time that it takes to get to that part. We also know things like the concentration of that intermediate, which allows us to inform how much of the second material has to be implemented, and then finally the loss of that second part. So we have a map of the steps that have to happen that allows the robot to sort of follow the outcome rather than the specifics. As was mentioned earlier today too, we are children of the pandemic. We do have a YouTube channel, so please like and subscribe. We have all of our sort of longer automation videos were posted up there too for review. What we're showing here is this amide bond robot whose job is not only to execute the chemistry, but if you notice, since the analytics are hooked up to the system, it knows what's happening at different steps. In other words, by charging one of the starting materials at a certain time, we don't have to inform the HPLC of when that peak might run out or where that specific database says that peak should show up. The system knows that by charging a starting material in this part of the workflow and a new peak showing up on the analytic must be correlated with the discrete signal of that particular material. So it's teaching itself how to interpret the results based on context. We couple that through, and what we end up is something that looks like this. So this is a reaction time course where the whole point of that experiment was actually just the tangential slope that we get right here. This was the data point that we were actually after, which is the rate of coupling in this second step. But what we've done by sort of delineating it out and having the entire database written like this, what we get is metadata on both sides of sort of the experimental purpose, where at the very beginning we have a calibration plot. So this is 2 charges of our starting material teaching the system what the peak is. We solve for the extinction coefficient so we can actually get to a quantitative result. We know that if we run this particular carboxylic acid again, and that activation profile doesn't change, we also have some data that says on a different day, a different batch may run a different way, and we'll know why there's a difference in that particular part. As well, at the end here, another calibration of one of the other intermediates built in. So what we get is something that looks more like the reading frame of a gene rather than a simple plot or single data. We're actually using this to visualize data in multi-dimensions. So the other side of this too is that's all well and good if people have the exact same hardware that I do. However, working on this means that we have to work as a global community. Reproducibility in different places means that we need standards to allow any outcome from one lab to be replicated somewhere else. So this is a project actually in collaboration with Lee Cronin at the University of Glasgow. What he worked on is an idea of this universal programming language for chemical synthesis known as KDL. And really what it does is break down those abstract steps such as wash, crystallize, transfer into a sort of person-readable Python-like code. And then that's represented, that's the sort of the instruction layer. But on top of it, locally to a particular piece of hardware, is a graph representation of that particular synthesis robot. So where chemistry moves, the valves, all of that is described locally. So really this is very much like I have a Mac, you have a PC, but we have local drivers which allow those pieces of hardware to interpret another program such as Doom or something like that, a game, where both PCs, regardless of the exact kind of hardware, could operate the same part. So we showed off in this Nature Synthesis paper 2 different approaches. One of them is kind of the Apple architecture, a closed hardware system, where very similar hardware in 2 places, what we're doing is we're changing code. So this is where a closed hardware ecosystem uses common data to move and optimize the synthesis between 2 places. So our lab would run some code, send it over to Lee's lab. Lee would run the same code, tweak it and optimize it, and using a GitLab type of an approach, we could go back and forth and come to an optimal synthesis. The other more open architecture, the sort of PC or Android architecture, meant that many different pieces of hardware had to run the same code. So this is where we have very different things like translocation with the cobotic arm, XYZ gantry on an Opentron, or the sort of more bespoke computer could all run the same synthesis. So single KDL, but the difference here is that the graph that describes each one of these synthesis ones is unique to the hardware platforms themselves. So we took this live. In this particular example, we have a multi-step synthesis where we did this example of a single graph that represents the hardware in 2 different places. Going through and doing this optimization, we came up with yields and purities that after a sort of, again, this 2-site optimization, we were able to agree on the same point. Most importantly, what we could have is teleportation of that data between different sites, which allows multiple groups with multiple specialities to optimize the hardware differently in their own space and time. The other one is, again, this is where we have very, very different hardware. So in our system, we have the Canova robot. So this is the sort of translocation arm. Here, the computer is really more about valving and tubing. But here, what's interesting is a single action, saying add in this KDL language, Over here in the computer, add means a very particular movement of valves and syringes. Over here, add means pick up the mobile dispenser, go and pick up and aspirate, and then dispense somewhere else. Again, that local representation is handled on its own, but the higher level abstraction of add is common in both cases. Now, what we can do with this is apply our variational feedback control. So once again, small differences in either temperature, reactor heating, and things like that are all coupled. So the example I showed you at the beginning gets baked into here, where time to completion becomes something that's actually in the KDL step. So instead of hard coding, run this for 45 minutes, we give it an outcome or an endpoint where the analytics actually guide when the reaction is done or what actions to actually take. The last point to bring up, though, is that there is a huge call to action in this space. We've all been working over the last 5, 10, 15 years to really accelerate what's happening. It's been this wonderful groundswell of hardware development, software development, and chemistry. The challenge, though, is that even for something as simple as this is the multi-step synthesis that we took. And if we said we have a target molecule, this particular ligand, there's a bunch of other data and computational ways to do synthesis planning and say this is a route to potentially make this one. However, there's many possible ones. So for example, this one precursor could be transformed forward to the molecule we want from these two starting materials. And this is something that's well documented in the literature. However, it's only domain knowledge that could look at this and say, well, that's actually not as much of an automation-friendly step because of the chemistry that could go wrong. These byproducts and things that we see in our documented literature right now are not something that actually make it into the training models. And it's just because usually representation in our literature is biased towards success. This was part of what we saw in one of our DARPA programs recently. Turns out organic chemistry works in 5% yield increments in high points just by doing a data scrape. What you see is a bias towards these points where things like these byproducts, which are domain-specific knowledge, do not make it into training sets. And as people sort of enter this space, what you miss is the opportunity to say, you know what, actually it's better not to follow what might the first representation is. This is the classic problem of a Dunning-Kruger curve, where misinformation sort of comes in just based on, again, a lack of full understanding of the overall system. So really, with that, what we've done is come a little bit closer, piece by piece, to true chemical teleportation. And again, it's this aggregation of hardware, standardization, and data formats. And again, it represents a lot of what we've been talking today about flexible automation and adaptation. And just a quick note, a paper that's actually out today. Really what this does is it all comes together with this particular project. This was a DARPA project where 6 teams in very different locations were able to bring their skills together to not only design, synthesize, test, and then actually scale up this organic laser emitter for testing as a new material. This is a project led by Alon Asper-Guzik, and actually one of the cornerstones of what led to the creation of the Acceleration Consortium. But it's the first sort of example of how many different disciplines can collaborate across a very large geographic space, and also with very different hardware and very different points. So as a general sort of strategy, I'd really encourage you guys to take a look at this. It's something that we're very proud of as an outcome for what we've been trying to build for the last couple of years. So with that, again, wonderful to have the opportunity to speak to you guys, and looking forward to the discussion and poster sessions throughout the day. Thank you very much, guys.
Thank you, Jason. That was a lovely talk.